Building on the example we just did, let's change from vectors to transformations. So we had these three vectors in R2. They were linearly dependent, but I can think of them as transformed basis elements. So I'll just TE1, TE2, TE3, the three columns of my matrix. So E1, E2, and E3 go to those three vectors. Now we can make a null space from our linearly dependent list. 2 of the first, 3 of the second, and 1 of the last made the 0 vector. I'm going to write that as a matrix vector product. And T, acting on that vector, is 0. It's a null space vector. Use the dependence lemma. N goes in, E3 comes out, because E3 is the last one on the list. But I can think of those vectors as transformed standard basis vectors. So there's the columns of another transformation, taking the standard basis to the basis we want. But that I can think of as a transformation from R3 to R2. I just got to follow the links. So first column is where E1 goes. E1 goes to 0, 0. I'm not changing anything in the output space, and so I'm just using the identity matrix to connect. The I matrix. Basis elements are basis elements. So there's the first column of my matrix. Now take E2, goes to E1, transformed into 1, 1. Identity, and that's our second column. And I do the same for E3. Goes to E2, transformed E2, 1 minus 1. And there's the third column of my matrix. This matrix has been B, then T. B, then T. Now I'll remove all the vectors and make a commutative diagram. So there's our commutative diagram. The identity matrix doesn't really need to be in there, so we can do an alternate notation. So we're just transforming into R2 from R3. We're changing the basis only in the domain. And so we have a new transformation, B then T.